everyone, welcome back. Today we are going to finish up Unit 3. I know it's been a long unit, but we've done multiple lectures on rivers and groundwater, and most of this unit is very specific to South Louisiana. So this lecture today is a little less specific to South Louisiana because we're going to start off by talking about glaciers. But then we're going to segue into ice ages, so that's going to bring up climate change, and then we're going to end the lecture today talking about sea level rise and how sea level rise accompanies changes in climate. So it's going to start with part of geology that's not very familiar to us, but we're going to get there in the end. We're going to kind of segue to it in the end. So the first thing that we're going to talk about today is glacial geology. Now, obviously, we don't have a lot of this around here, but if this class was being taught in Minnesota or Maine or somewhere in Canada, then we would be talking for several lectures about glacial geology because there are a lot of these features that are very unique to moving glaciers, to glacial meltwater, these little small lakes that form because of glacial meltwater. So all of this geology that's very specific to the glaciers themselves. So first, let's define glacier. A glacier is just a large, long-lasting mass of ice. It has to last essentially not just a year, but for several years. It can't be a seasonal feature, and that it moves downhill under its own weight. So in that sense, glaciers are essentially sort of the frozen equivalent of rivers in places or in time periods like during ice ages where you don't have flowing water across the surface because it's too cold. You're going to have snow build up and accumulate and never melt. And therefore you have a large weight of ice that's going to be moving downhill under its own weight. And it has this tremendous capacity to change the landscape, to essentially erode or cut through all of the layers of vegetation and soft soil, soft sediment, and gouge out the landscape. And so this ends up being very unique in geology because in places like South Louisiana that never see glaciers, not even during ice ages, we don't have any of this kind of geology at all. So as it turns out, most of the world's fresh water, not water in general, not including salt water, but fresh water is locked up in the form of ice, even today, even after 50 years of climate change. In the future, it might be a little bit of a different proportion, but still the majority of the fresh water on Earth will be locked up in the form of ice, in the polar ice caps and in alpine glaciers. So the glacier itself, a feature called a glacier, is going to develop as snow is compacted and recrystallized. And in that way, we can very much relate it to the process of forming maybe metamorphic rocks or sedimentary rocks. We know we start off with this loose, unconsolidated, almost sort of powdery stuff. In the case of a glacier, it's the snow. In the case of something like a metamorphic rock, we start off with clay or mud or sand. As that material is then deposited and buried, it undergoes pressure, and that pressure causes it to be recrystallized. In the case of a glacier, that recrystallization is going to form a hard mass of ice that's going to be crystalline, essentially. It's going to be interlocking. It's no longer loose, powdery snow. In the case of metamorphic rock, you might have the recrystallization of that sediment occurring under much higher temperatures and pressures, causing that rock to completely recrystallize, and you might form something like quartzite from what was once sand. So you go from snow to this granular, harder packed snow to this stuff called glacial fern, and then finally glacial ice, which is completely recrystallized. Now, it's extremely important to remember that if the snow actually melts during the summer months, if that material just goes away, it's no longer a glacier. A glacier has to exist throughout the entirety of one year and to the next in order to have enough snow compacting to actually flow downhill under its own weight and to do a substantial amount of erosion. So today, under this interglacial period we're in, we're between two ice ages. We have glaciers only under the following conditions. We have alpine glaciers, or mountain glaciers, where your land elevation is high enough for the temperature to be cold and to stay below 32 degrees Fahrenheit throughout the entirety of the year, and that allows for the snow to accumulate year after year. Or you have glaciers only in your very, very high latitudes in your polar regions. So this is far north of the Arctic Circle and Antarctic Circle. This is very, very close to the poles. This isn't in places where you might just get some snow, like places like Ohio and Maine today. You get plenty of snow there, but it all melts back over the summer, so those aren't glaciers. So your continental glaciers are the ones that form at sort of normal elevations, not very high mountainous elevations, but at high latitudes close to the poles. Those are your continental glaciers. And your alpine or mountainous glaciers are going to form only at your high elevations. So you can have glaciers forming, let's say at Pikes Peak or Mount Kilimanjaro or Mount Everest fairly close or much closer to the equator than you would if your elevation wasn't high, just because your temperatures remain very, very low at your high elevations. So when you're dealing with losing glaciers, and this is definitely a topic of concern today when we're talking about, climate change and sea level rise and the effect of glacial ice on all of these things, you're only going to have glaciers recede and change only when temperatures allow for more melting than snow accumulation. So maybe in some cases some snow melting is always going to occur, but it can't vanish the glaciers altogether, or it's no longer a glacier. If some melting occurs, but that melting is then buffered by snow accumulation, then that glacier grows. If the opposite occurs, if you have more melting than the accumulation of snow during the winter months, then that glacier will end up receding over time, eventually potentially vanishing altogether. So in Glacier National Park, the moral of the story is that if you want to actually see glaciers in Glacier National Park, you better go pretty soon, because the sort of before and after pictures of just the last 30 to 40 years of change of those glaciers is pretty damning. You have these large glaciers in place in, this one picture that I have on the left from 1913, and the more recent picture from 2005 on the right shows this glacier basically as a non-existent feature. There's only just a very small amount of ice that's still there. So the next thing that we're going to talk about is essentially sort of what happens as the glacier moves and how erosion and deposition is going to occur with the glacier. Now, okay, to kind of tie all this together, we're thinking about the glaciers the same way that we talked about the rivers. It's not the glacier itself that's important, it's its capacity to change the landscape. And the way that change in the landscape occurs is through erosion and deposition. So while rivers are going to flow faster at the bottom, slower at the top, and move bedload sediment, suspended load sediment, all that good stuff is going to happen, glaciers are essentially going to do something that's a little bit different. They're actually going to flow faster towards the center and towards the middle, so up at the very top of the column of ice. That's where the fastest moving ice is going to be. And then you're going to have slower moving ice at the margins, at the base of the glacier and at the sides of the glacier, where all of that friction is going to inhibit that ice to actually flow any faster. So still, we're dealing with very, very slow speeds of movement, but it doesn't mean that it's ineffectual at doing erosion and deposition. If anything, glaciers are more successful at eroding sediment and depositing sediment. They're effectively sort of nature's bulldozers. They just happen to be very slow-moving bulldozers. If you were trying to tell somebody that they're moving entirely too slow and that they need to start moving faster, you might say that they're moving at a glacial pace. And that's a very apt metaphor, because glaciers, especially in comparison to rivers, are going to move at an incredibly slow pace. So moving faster in the center, slower along the margins, they're going to be carving out their landscape, carving through vegetation, soft sediment, soil layers, and really just leaving behind just the bare bedrock behind. So one other thing that they do is as they move, they're going to, in addition to peeling back the vegetation and soil and soft sediment, they tend to erode and break off big chunks of the rock as they flow through in a given environment. And these rocks then become embedded at the margins of the glaciers and will scrape through the bedrock. So it's very common to see evidence of past major glaciation events and major ice ages in places where you may not have ice ages today. And one of the best pieces of evidence that we have are the striations, the glacial striations that are left behind in the rock. This is essentially evidence that you had an enormous weight of ice, maybe even 2 to 3 times the height of the Empire State Building, moving through a given environment and scraping along that environment and kind of giving us sort of an arrow pointing in the direction that that glacier was moving in the past. So to give you an idea of the power of these glaciers, I wanted to show you this picture on the right-hand side. And that picture is of an outcrop of basalt in Central Park in New York City. It's sort of the last place on Earth that you would expect to see really interesting geology. But even here in the middle of a concrete jungle, we have really interesting geology to look at. So if you've ever been to Central Park, there are these sort of outcrops of basalt that sort of just exist all over the place. They sort of pop up out of the grass like little islands in Central Park. And this basalt is basically sort of unchanged since the last major ice age that ended 10,000 years ago. So this basalt is very, very jagged on the surface. It has all of these glacial striations. So at the time when ice was in what is now modern day New York City, that ice was 2 to 3 times the height of the Empire State Building today. It pushed through Central Park and it carved into this rock below, kind of giving us sort of that arrow of I was a glacier, I was here, and I was moving in this direction and carving through this landscape. So it's some of the most interesting geology that you'll see in a major city anywhere in the United States. So now we're going to move on to some other glacial erosion that takes place, but this is going to be specific to mountainous or alpine glaciers. When you have glaciers existing in mountainous regions, you're going to have most of that ice present at the higher elevations, and then that ice is going to then be moving downhill. So the first thing that tends to form is going to form because of the weight of all of this ice eroding into the mountain peaks themselves. These sort of circular bowl-shaped erosional features are going to form as a result of all of that weight of ice starting to erode down into the peaks of the mountains. And these are called glacial cirques. So in places like the very top of the Front Range of the Rockies, and places like the Swiss Alps, and other places where you have alpine glaciers existing, this is not very unusual geology to see at all. Very, very ragged, harsh, jagged mountainous peaks that are going to have these circular bowl-shaped depressions that had been formed from the weight of all of that ice. When you have several cirques all carving back into the same mountainous peak, you can have these sort of flat features called arêtes form, or you can even have glacial horns. The Matterhorn in the Swiss Alps is one of these features, and it's essentially several glacial cirques all carved back into that same peak, leaving you with just this almost sort of finger pointing up towards the sky thrust out of the earth itself. The other thing that's going to happen as that ice from the cirque is then going to flow down the mountain excruciatingly slowly, is you're going to have valleys form from this ice, but they're fundamentally very different valleys that tend to form from rivers. Rivers tend to form V-shaped valleys because remember, the fastest moving water at the bottom of a river channel is going to be essentially sort of moving the slowest, and that's going to be where all of that gravel and all of that sand and so on is going to be sort of bouncing or rolling or sliding along the bottom of the water channel. So you typically have these pointed V-shaped valleys. Now, those V-shaped valleys are going to be a little bit different if you have ice then flow through that same valley. So let's say circumstances change, we enter into another ice age where there were once V-shaped valleys, you would instead have these U-shaped valleys. So in these U-shaped valleys, you have all of this glacial ice carving a wide swath at the bottom of the channel itself, and that's why you get the U-shape instead of the V-shape. Now, the other thing that tends to happen when rivers carve out their terrain is that in addition to V-shaped valleys, you often get things like canyons forming. You really don't get canyons forming when you have moving ice at all. It tends to be more narrow features. You don't typically have canyons because the conditions are not really going to be right for canyons to form. You end up instead having these smaller features still, but still U-shaped valleys. So the U-shaped valleys that we have across the United States that you don't even really think of as being glacial features include things like the Great Lakes, the Finger Lakes of upstate New York, all of these features that are now places where freshwater exists in the continental interior, but under an ice age, these were places where glaciers moved through the landscape and eroded out the landscape. One thing that's so important to remember here is to kind of take into account how the sediment is actually moving. The glacier's capacity to move sediment is going to be essentially the same capacity that a bulldozer has. A bulldozer can move any size sediment, boulder-size sediment, sand-size sediment, clay. It can move anything. A river's capacity to move sediment is going to be dependent on how fast it's flowing. A slow-moving river might only be able to move mud or clay, while a faster-moving river might be able to move sand, boulder-sized particles. So depending on flow velocity for rivers, and it's going to just be that any glacier has the capacity to move basically any size sediment, particularly when you're dealing with massive glaciers. And if you can move that sediment, you can ultimately deposit that sediment. A glacial deposited sediment is largely unsorted, unlayered, and typically referred to as glacial till. Till is just the name for that sediment itself, that unsorted, unlayered, gigantic pile of sediment. And still, conjure up that picture of a bulldozer being completely indiscriminate in what size sediment it's moving. A glacier is going to do the same thing. So the sediment itself is the till. The feature that's created from that pile of till that gets left behind is called a moraine. As U-shaped valleys form and as the glacier moves downhill, eventually it starts to pile up sediment on the edge of the moving glacier, kind of almost building up its own valley walls. Those are called lateral moraines. And once the glacier extends so far down a mountain that it enters into a point where it starts to melt, that ice melts away, and whatever sediment was left behind at the edge of that moving glacier is called an end moraine. But regardless, if it's glacial deposited sediment, it's going to form this feature called a moraine. The last thing that forms as a result of glacial deposition, so prior to this, we've been talking about glacial erosion, and then glacial deposition is the till, the moraine, and finally the glacial outwash. As a glacier gets to this point where it's either extended so far south or so far down a mountain that it gets into warmer conditions, it loses all power because it melts. And as it's melting, it builds up its own features. Things like ground moraines and kettle lakes and these sort of larger lakes that are all fed by these rivers. You typically have sort of these braided stream channels because you have an unbelievable amount of sediment and not a tremendous amount of water. So instead of having one main channel, you have several small channels that tend to kind of flow in and out of each other. These are all examples of features that are formed from glacial outwash. So, as you've kind of gotten the idea so far, glacial geology is very important to the northern part of North America, the northern United States, and in Canada. It's not incredibly important to us, at least now, but it has been in the past, because even while we don't have a tremendous number of glaciers under conditions right now, we did around prior to 10,000 years ago. At its height, it was about 18,000 years ago. We were in the middle of the last major ice age. So that was the last major ice age, and we've had thousands of ice ages prior to just the last major ice age. Sometimes they're more severe, sometimes they're less severe, but they're most importantly going to impact the areas around the North Atlantic Basin, places like the northern part of North America and northern Europe. So we know that climate has changed. And it has changed because of natural cycles, because this is all before human interference was possible. We also know that climate does change because of human interference and has changed over the last 50 years, will continue to change into the future. It's very important that you remember that these are completely, really sort of separate cycles. What gets us in and out of ice ages and what is driving our modern day anthropogenic climate change or man-made climate change. So we'll talk a little bit more about man-made climate change later, but now let's just talk specifically about ice ages. The theory of ice ages states that in the past, conditions were both colder and wetter in areas surrounding the North Atlantic than conditions are today. And so it's definitely roughly every 100,000 years, and then getting into smaller cycles roughly every sort of 20 to 40,000 years, we've dipped in and out of these ice age cycles. Right now, we would be considered to be in an interglacial period between ice ages. But even as recently as 10,000 years ago, we were just getting out of a glacial period or an ice age itself. So the most important thing that we have to cover today is why the ice ages occur, why we have this cyclicity. That cyclicity started about 2.5 million years ago. And geologically speaking, 2.5 million years ago was a time that was incredibly important for North America. This was the point in geologic history in which North America and South America became connected by this land bridge. Overflowing volcanoes in what is now modern-day Costa Rica and Panama created the Isthmus of Panama, created the land bridge that connects North and South America. Now, that in itself isn't the absolute driver of getting us in and out of these ice ages. It's the change in ocean circulation that resulted. So prior to the formation of this land bridge, water could circulate from the Atlantic, flow directly almost across the equator into the Pacific Ocean. Now, with that land bridge connecting North and South America, water has to go all the way around the southernmost point of South America to then get into the Pacific Ocean. So what happens as a result is that we typically get more warm water flowing up into the Gulf of Mexico, up the eastern seaboard, and getting into the Arctic Ocean than we had in the past prior to 2.5 million years ago. And that allows this region to have a greater sensitivity to any other factors that are going to get us in and out of climate change. So that's sort of the first set of circumstances, the Isthmus of Panama, that creation of the land bridge connecting North and South America, and changes to ocean circulation. That sort of gets everything started. Then the factor that actually dips us in and out of ice ages, because we now have a greater sensitivity to this, is this thing called Milankovitch cycles. Milankovitch cycles are a blanket term introduced by a mathematician named Milutin Milankovitch that accounts for all of the major changes that Earth goes through in space over really long periods of time. Now, we're already familiar with the short-term things that Earth does in space. It spins on its axis, and that's why we have days. It orbits around the sun, and that's why we have years. In addition to these, the Earth also tends to wobble around on its axial tilt. Its axial tilt actually changes in angle ever so slightly, and the shape of the Earth's orbit actually changes over time. And these are the three main factors that are part of the Milankovitch cycles. We call the changes in the shape of the Earth's orbit, changing from a slightly more circular orbit to a more elongate elliptical orbit, we call that eccentricity. It operates on a roughly 100,000 year time scale, and it affects climate because it affects our distance between the Earth and the sun. We call those changes to the axial tilt of the Earth obliquity, and it ranges from maybe Earth having a 23.5-degree tilt like it does today to all the way to a 24-degree tilt to a 22.5-degree tilt. So that's only an overall change of like a degree and a half. A degree and a half of overall change of axial tilt. But that has a pretty drastic effect on climate because the more tilt the Earth has, the broader the sweep of seasons are across the Earth itself. And so if you have more extreme seasons, then you have conditions where it can get hotter and colder at various points during the year at the extremes of the Earth. So all of that has an effect on seasons. So that's obliquity. The last of these is the Earth sort of wobbling around on its tilt. So that's different than the change of the axial tilt itself. The change of the axial tilt is just saying how much is the rotationary axis of Earth tipped over. Is it tipped over a lot or is it tipped over just a little bit? So that's rotationary axis is the axis that the Earth spins around. The precession is the direction in which that axial tilt is pointed. So right now, for instance, our North Star is a star called Polaris. It's the one that is on the northernest part of our horizon at night. And it's a very bright star, so that is our North Star. In another 13,000 years or so, the Polaris star won't be our North Star anymore because Earth will be oriented in a different direction in space. A star called Vega will be our North Star. So it's very similar to a spinning top. Right when you start a spinning top, it might be spinning really, really fast and might be spinning perfectly vertical with respect to the surface that it's spinning on. But over time, that spinning top, as it starts to slow down, is going to kind of wobble around on its tilt a little bit. And as it wobbles, that is the precession of that spinning top. And so that's what the Earth is doing. It's sort of wobbling around on that tilt very, very slowly. The key to all of the Milankovitch cycles is that all of these are going to very, very slowly affect climate. The quickest of these cycles is the precessional cycle, and that takes 22,000 years to undergo a complete cycle. The longest term is the eccentricity cycle, which takes 100,000 years to undergo a complete eccentricity cycle. So these factors all work on their own timescales, but when they all sort of add up together, you know that's going to be a really extreme ice age. When they're conflicting a little bit, but one of the more powerful forces is going to be sort of overtaking the other, that might be a minor ice age. And when all of those factors allow for conditions to be warmer in the North Atlantic basin, then that's going to be when we're in an interglacial period. And that's where we are today. We are in a period between two ice ages, and it's not a coincidence that the entirety of human civilization took place in that time period that happened to be warmer between those ice ages. So let's look at some of the effects of past glaciation across North America, because they are going to include features that you never would have considered to be glacial features. Some of the first ones that we're going to talk about are the large lake basins, like all of the Great Lakes and the Finger Lakes of upstate New York, and you're seeing that on the right picture on the right. All of these lakes are essentially giant U-shaped valleys, and once all that ice melted, they formed the Great Lakes that we have today. Now, those lakes are separated by lateral and end moraines. So you have all of this high elevation separating the Great Lakes. And so that's what actually contains all of that fresh water into those lakes today. And it's a very similar thing that separates out all of those Finger Lakes of upstate New York. So those are sort of direct, slightly more obvious effects of past glaciations. The less obvious effects include the saltwater lakes of the western part of the United States, most notably Salt Lake, the Great Salt Lake, as in Salt Lake City, Utah. So if you go out there today, there's only a very small amount of water, and there's a tremendous amount of salt deposited in layer after layer around the Great Salt Lake. At some point, this wasn't really a salt feature at all. This was a much, much larger freshwater lake. But then as conditions dried out in this interglacial period, that we're in now, that water then evaporated away. Once that water evaporates away, all that's left behind is a little bit of water and mainly a tremendous amount of salt. So even a freshwater feature originally contained a little bit of salt, and then as that water evaporates away, you have a saltwater feature, a salt lake in the interior of a continent. The same is true for Mono Lake, California, except in that case, almost essentially all of the water has evaporated away, leaving just salt deposits behind. Now, for us in South Louisiana, the most notable effect of past glaciations and comparing that today has been the effect of where the coastline is and what happens to sea level as you change from a glacial period to an interglacial period. Sea level would have been much, much lower than it is today during an ice age, during a glacial period, and if conditions were warmer than it is today, sea level would be much, much higher. So to give you an idea of what this actually looks like, I'm going to show you 3 pictures. The first picture is what sea level looked like and what North America looked like during the last major glaciation event. This is the Laurentide ice sheet and that associated glaciation event, which puts us at around 120,000 years ago. So at this point in the past, this is far before human civilizations were on Earth, we have a much, much lower all sea level. The most obvious part of this picture, of course, is the tremendous amount of ice that's on the northern part of the continent, especially the northeastern part of the continent, because you had not only colder period of time, but a wetter period of time, so more snow, more ice accumulating. And at this point, you had ice that was higher than 2 to 3 times the height of the Empire State Building. So you had thousands of feet of ice on the northern part of the North Atlantic, of the North American continent. You can also see in this picture, this first picture, all of these big freshwater lakes existing in the western part of the continent that obviously aren't there today. Most importantly, take a look at the Gulf Coast region, where it doesn't look like a whole lot of action's taking place. But there's just something that feels a little bit wrong in this picture. If you look at the state of Louisiana and you look at the state of Florida, everything looks a little too fat on this picture. Everything looks like that coastline is just a little bit too far out, and it is, because the coastline was almost 100 feet lower than it is today. So this is the glacial picture, and then let's change to what it looks like today. When you went from that first picture to that second picture, you can see how sea level increased, particularly if you were looking at the Gulf Coast region when that happened. A lot more of that light blue that edges around the continent, that tends to sort of pop up because that's all that continental shelf, that place that represents sea level low stand along the edges of the margins of the continent. Okay, so that's what it looks like today. Now we're going to project a potential point in the future. Now, in order for this to happen, we would have to have an almost ridiculous, unprecedented, runaway greenhouse effect occur on Earth. But this is just a hypothetical point in the future that would occur if all of the polar ice melted on Earth. It is not what the IPCC, the Intergovernmental Panel on Climate Change, is actually projecting will happen in the future. I just want you to see sort of what is the maximum extent, what is the highest point that sea level can actually reach. So this picture shows you what sea level would look like if all of the ice on Earth melted. And that would be a total rise in sea level of 212 feet. Most notably, take a look at Louisiana in this picture, which essentially just vanishes. Almost the entire state of Louisiana, even northern Louisiana, Shreveport, Monroe, they are far below this point of 212 feet of elevation above sea level, so they would be susceptible to this as well. Now, not only South Louisiana would be vulnerable to a rise in sea level like this. Essentially, all of these major coastal cities would essentially just be gone under these conditions. So all up and down the East Coast, places like New York and Philadelphia and Miami, they're gone. Even down the West Coast, where elevation is higher, places like San Francisco and Los Angeles and San Diego, they're gone as well. Now, this is the sort of ridiculous scenario. This is 212 feet of sea level rise. And particularly in the next 100 years at the next 100 years from now, nobody's forecasting a 212-foot rise in sea level. But a sea level rise of 3 to 5 feet in the next 100 years would have its own very catastrophic effects on some of these same cities that you're seeing being completely obliterated by this 212-foot rise in sea level. So let's sort of round out the lecture today talking about climate change and the effect on sea level of climate change. Now, atmospheric temperature change will absolutely lead to a change in sea level. We see that when we go from a glacial period to the interglacial period that we're in now. And if we extend that further, if we're talking about going from that interglacial period to a much warmer world as a result of atmospheric temperatures rising, then we see that sea level rise again. Now, the reason why atmospheric temperatures are rising and have been rising for the last 100 years, will continue to rise in the future, is because of the burning of fossil fuels and deforestation, and the effect that that introduction of CO2 has on the atmosphere. CO2 is a greenhouse gas, so as heat gets into the Earth's atmosphere, it heats up the surface, and then that infrared radiation can't escape back out into space. It becomes locked into the lower Earth orbit and close to the surface of the continents because those greenhouse gases are keeping it there, much like the glass roof of an actual greenhouse keeps heat within the greenhouse itself. Now, so we already know that that is taking place, that the temperatures in the atmosphere are increasing, they're getting warmer. Sea level rise absolutely accompanies that, because as the temperature in the atmosphere warms, so too does temperatures in the ocean. And when you increase the temperature of ocean water, two things happen. The actual space that water takes up is going to increase. The volume of water in the ocean is actually going to increase just because temperature has risen. The more you increase temperature, the more volume that water actually takes up. So water's expanding when it's warm. Plus, glaciers are melting, and not just sea ice. So when you melt sea ice, you don't have a very drastic increase in sea level as a result of that sea ice melting. But when you melt continental ice, and then that continental ice is melting and returning out into the oceans, you absolutely do have an effect on sea level that accompanies that. So, as it turns out, half the world's population lives near sea level, and quite a bit closer to sea level than 212 feet above sea level. We're talking about so close to sea level that even something like a 5-foot change in sea level has a pretty catastrophic effect on these people and on these populations. So, the forecasting for the future of what a kind of atmospheric temperature change that we're going to have and the accompanying change in sea level comes mainly from an organization called the Intergovernmental Panel on Climate Change. So that's where you're seeing in the next several slides, IPCC, Intergovernmental Panel on Climate Change. Every 4 or 5 years or so, they release a new report. So this is the 2013 report. And what you have here are basically the historical changes in surface temperature, sea level, and so on the left-hand side of the picture. And on the right-hand side of each of these graphics, you have scenarios of how things could change in the future, depending on different criteria. So you have sort of a best-case scenario and a worst-case scenario. In this graphic, the best-case scenario is in blue and the worst-case scenario is in red. So even under the best case scenario, we have some change in atmospheric temperatures occurring. And if you have an atmospheric temperature change occurring, you absolutely have an accompanying change in sea level. Even under the best case scenario. And obviously under the worst case scenario, it becomes much, much worse over time. So what's sort of forecasted to happen here with this, with regard to sea level change, is essentially a sea level change in the next 60 to 70 years, not that far in the future, 60 to 70 years of 3 to 5 feet of sea level change. Now, I'm 5 feet, 4.5 inches tall. So we're talking about a sea level change that's not even as tall as I am, but you would be shocked at how much of the coastal areas of the world, and particularly the coastal areas of South Louisiana, would be tremendously vulnerable to something like 3 to 5 feet of sea level change. And to give you an idea of what that change would mean to South Louisiana, I have a couple of pictures for you of sort of hypothetical scenarios. The first one is a very, very heavily photoshopped, obviously, picture of Tiger Stadium, Death Valley. So this is Baton Rouge on the right-hand side of this picture, and then you have sort of this idea that this is now beachfront property. So what I want to kind of get you thinking of right now is what scenario would actually allow for Baton Rouge to become beachfront property, to become a coastal city? Is it 3 to 5 feet? Is it 50 feet? Is it 100 feet? So it's also sort of a question of how well do you know your own elevation, where you're living? So here's a map, and this is a hand-drawn map. These next few pictures were drawn by my former advisor at LSU, Dr. Jeff Hayner. This is a hand-drawn map of South Louisiana with the accompanying coastline as we have it today. Now, the first picture I'm going to show you is of what the coastline would look like with only 5 feet of sea level change. So again, that's the same increase in sea level of my overall height. And this isn't even taking into account the problems that we have with coastal subsidence in South Louisiana, sinking of the ground surface because of all of these faults. This is just purely taking into account global sea level rise. This is what South Louisiana would look like with 5 feet of sea level rise. Obviously, New Orleans is gone, Morgan City's gone, Homa's gone, or nearly gone, Grand Isle's gone. All of these places are below 5 feet of elevation above sea level. Even with an extensive amount of engineering currently surrounding the city of New Orleans, and even more engineering in the future, the best you could potentially hope for would be this heavily leveed bowl that's well below sea level of New Orleans, which even under the best engineering in the world would still be an incredibly vulnerable city. So we don't quite have that picture that I showed you in the past of New Orleans. Of Tiger Stadium as beachfront property. That would be a 25-foot rise in sea level. So once most of South Louisiana, the coastal part, and the marshes of South Louisiana, and places like New Orleans and Homa are underwater, they're a lot more vulnerable than, let's say, we are on the North Shore and places like Baton Rouge are. So that kind of gives you an idea of just how vulnerable we are specifically. In other major cities, it would take a similar rise in sea level to very much compromise those cities. Places like New York, Los Angeles, Miami, Houston would all be in a very dire position with even 5 feet of sea level rise. Okay, so we're going to wrap things up today by taking you on a little field trip that's going to show you some of these issues with sea level rise in South Louisiana. So we're back again at the Turtle Cove Research Facility at Pass Manchac. You may remember a few lectures ago I did an interview with Dr. Blanchard out here, out in the marsh behind the Turtle Cove facility. I thought this might be a good time to give you a little bit to consider as far as how sea level rise accompanying global warming could affect you personally in Louisiana. Now, all of that marsh grass that we saw from a few lectures ago, that marsh grass is highly dependent on this exact proportion of fresh water to salt water, not too much salt water. When you have sea level rise, of course, you're going to have salt water intruding into those areas and compromising the grass. When that grass gets compromised and that grass dies, then you lose what's really sort of holding all of that ground in place. And then ultimately that marshland becomes open water like what you're seeing behind me. So this is something that's really, really important for South Louisiana, particularly for areas south of here, south of New Orleans and all of the marshland along the coastline itself. So keep in mind that in the next 50 to 100 years, we may see 3 to 5 feet of sea level rise. And we would be looking at a very, very different area right here around the Turtle Cove Research Facility.